Hello and welcome to the series of e-learning module on uniform distribution. In this module, we will cover the definition of uniform distribution through probability density function, understand the distribution function, moments, moment generating functions, median and mean deviation. By the end of this session, you will be able to describe the definition of uniform distribution through probability density function or PDF. Understand distribution function. Explain moments, that is mean and variance. Understand moment generating function. Describe median and understand mean deviation. A continuous random variable x is said to follow uniform distribution in the interval a, b if its probability density function is given by f of x is equal to 1 divided by b minus a, 0 less than x less than 1, and we write x follows uniform a, b. Here, a and b are the parameters of the distribution. In particular, if a is equal to 0 and b is equal to theta, then we can write x follows uniform 0, theta. If a is equal to minus theta and b is equal to theta, then x follows uniform minus theta, theta. Hence, we can define uniform distribution for any two constants a and b. Remarks. Consider some remarks. A and b, a less than b, are the two parameters of the distribution. The distribution is called uniform distribution on a, b since it assumes a constant or uniform value over all x of a, b. The distribution is also known as rectangular distribution since the curve y is equal to f of x describes a rectangle over the x-axis and between the ordinates x is equal to a and x is equal to b. Now let us find cumulative distribution function or distribution function. The cumulative distribution function of the uniform distribution on a, b is given by f of x is equal to integral from a to x f of x dx. This is equal to 1 divided by b minus a into integral from a to x dx, which is equal to 1 divided by b minus a into x ranges from a to x. This is equal to x minus a divided by b minus a. Hence, we can write f of x is equal to 0 for x is less than or equal to a. X minus a divided by b minus a for a less than x less than b. And 1 if x is greater than or equal to b. Figure A shows the graph of PDF f of x and figure B shows the corresponding distribution function of the same. Now let us find mean of the distribution. If x follows uniform a, b, then the mean of the distribution is given by expectation of x is equal to integral over x into f of x dx. This is equal to 1 divided by b minus a into integral from a to b x into dx. By integrating, we get 1 divided by b minus a into x square divided by 2 ranges from a to b. This is equal to 1 divided by 2 into b minus a into b square minus a square. On simplification, we get b plus a divided by 2. Now let us find variance of the distribution. If x follows uniform AB, then the variance of the distribution is given by v of x is equal to expectation of x square minus expectation of x the whole square. First, let us find expectation of x square. Expectation of x square is equal to integration over x square into f of x dx, which is equal to 1 divided by b minus a into integral from a to b x square into dx. By integrating x square, we get 1 divided by b minus a into x cube divided by 3, ranges from a to b. This is equal to 1 divided by 3 into b minus a into b cube minus a cube. Using formula for b cube minus a cube, we get b square plus a into b plus b square into b minus a divided by 3 into b minus a. This is equal to b square plus a into b plus b square divided by 3. Also, we have found expectation of x is equal to b plus a divided by 2. Hence, variance is given by variance of x is equal to expectation of x square minus expectation of x the whole square. By substituting, we get b square plus a into b plus a square divided by 3 minus b plus a divided by 2 the whole square. Taking common denominator as 12, we get 4 into b square plus a into b plus a square minus 3 into b plus a the whole square divided by 12. On simplification, we get b minus a the whole square divided by 12. In general, moments of the uniform distribution with parameters a and b can be obtained as follows. Mu r dash is equal to expectation of x to the power r is equal to integral over x power r into f of x dx is equal to 1 divided by b minus a into integral from a to b x power r dx, which is equal to 1 divided by b minus a into x to the power r divided by r plus 1 ranges from a to b, which is equal to 1 divided by b minus a into b to the power r minus a to the power r divided by r plus 1. By substituting r is equal to 1 and 2, we can obtain expectation of x and expectation of x square and hence mean and variance. Moment generating function. Let us obtain the moment generating function of the distribution. If x follows uniform AB, then moment generating function of uniform distribution can be obtained as follows. Expectation of e to the power t into x is equal to integral over x e to the power t into x f of x dx, which is equal to 1 divided by b minus a into integral from a to b e to the power t into x dx. By integrating e to the power t into x, we get 1 divided by b minus a into e to the power t into x divided by t ranges from a to b, which is equal to 1 divided by t into b minus a into e to the power t into b minus e to the power t into a at t not equal to 0. Median. Let us find the median of the distribution. If x follows uniform AB and m is the median of the distribution, then integral from a to m f of x dx is equal to half is equal to integral from m to b f of x dx. Hence, we can get m by solving any one of the integral. Hence, consider integral from a to m f of x dx is equal to half. This implies 1 divided by b minus a into integral from a to m dx is equal to half. This implies 1 divided by b minus a into x ranges from a to m is equal to half, which implies 1 divided by b minus a into m minus a is equal to half. On simplification, we get m is equal to b plus a divided by 2. Observe that for uniform distribution, mean is equal to median. Since mean and median are same for uniform distribution, we can find mean deviation about mean or median, which are also the same. If x follows uniform AB, then mean deviation about mean is given by expectation of mod x minus expectation of x is equal to expectation of mod x minus b plus a divided by 2. This is equal to integral over x mod x minus b plus a divided by 2 into f of x dx. Let us take t is equal to x minus b plus a divided by 2, so that when x is equal to a, t is equal to minus of b minus a divided by 2, and when x is equal to b, t is equal to b minus a divided by 2. Therefore, mean deviation is equal to 1 divided by b minus a into integral from minus of b minus a divided by 2 to b minus a divided by 2 modulus of t dt. Since it is an even function, we can change the limits as 2 times 0 to b minus a divided by 2. Hence, we get 2 divided by b minus a into integral from 0 to b minus a divided by 2 t dt is equal to 2 divided by b minus a into t square divided by 2 ranges from 0 to b minus a divided by 2, which is equal to b minus a divided by 4. Results. Now consider the following result. Show that for a rectangular distribution with probability density function, f of x is equal to 1 divided by 2 into a, where minus a less than x less than a. Moment generating function about origin is sin h a into t divided by a into t. Also show that moments of even order are given by mu 2n is equal to a power 2 into n divided by 2 into n plus 1. Let us prove the result as follows. Moment generating function about origin is given by mx of t is equal to expectation of e to the power t into x, which is equal to integral from minus a to a e to the power t into x into f of x dx is equal to 1 divided by 2 into a into integral from minus a to a e to the power t into x dx. On integrating the function, we get 1 divided by 2 into a into e to the power t into x divided by t ranges from minus a to a is equal to 1 divided by 2 into a into e to the power minus a into t minus e to the power a into t, which is equal to sin h a into t divided by 2 into a. Now expanding for sin h a into t, we get 1 divided by a into t into a into t plus a into t the whole cube divided by 3 factorial plus a into t the whole to the power 5 divided by 5 factorial plus etc. till plus a into t whole power 2 into n plus divided by 2 into n plus 1 factorial plus etc. and so on. This is equal to 1 plus a into t the whole square divided by 3 factorial plus a into t the whole power 4 divided by 5 factorial plus etc. till plus a into t to the whole power 2 into n divided by 2 into n plus 1 factorial plus etc. and so on. Since there are no terms with odd powers of t in mx of t, all moments of odd order about origin vanish. That is, mu dash 2 into n plus 1 about origin is equal to 0. In particular, mu 1 dash about origin is equal to 0. That is, mean is equal to 0. Thus, mu r dash about origin is equal to mu r. Hence, mu 2n is equal to coefficient of t to the power 2 into n divided by 2 into n factorial, which is equal to a to the power 2 into n divided by 2 into n plus 1. On the x-axis, n plus 1 points are taken independently between the origin and x is equal to 1, all positions being equally likely. Show that the probability that k plus 1th of this point counted from origin lies in the interval x minus half dx to x plus half dx is nck into n plus 1 into x to the power k into 1 minus x to the power n minus k dx. Verify that integral of this expression from x is equal to 0 to x is equal to 1 is unity. Let us prove this result as follows. Here, x is given to be a random variable uniformly distributed on 0 and 1. Therefore, f of x is equal to 1, 0 less than or equal to x less than or equal to 1. Now consider probability of 0 less than x is equal to integral from 0 to x f of x dx is equal to integral from 0 to x1 dx is equal to x. Name it as 1. Therefore, probability of x greater than x is equal to 1 minus probability of x less than or equal to x is equal to 1 minus x. Name it as 2. Also, probability of x minus dx divided by 2 is less than x is less than x plus dx divided by 2 is equal to integral from x minus dx divided by 2 to x plus dx divided by 2 f of x dx is equal to dx. Required probability P is given by P is equal to probability that out of n plus 1 points, k point lies in closed interval 0 and x minus dx divided by 2. And out of the remaining n plus 1 minus k points, n minus k points lie in x plus dx divided by 2 and 1. And 1 point lies in x minus dx divided by 2 and x plus dx divided by 2. Name it as 3. On using 1, 2 and 3 respectively, we get P is equal to n plus 1 ck into x to the power k into n plus 1 minus k cn minus k into 1 minus x the whole to the power n minus k dx. Therefore, P is equal to n plus 1 factorial divided by k factorial into n plus 1 minus k factorial into x to the power k into n plus 1 minus k factorial divided by n minus k factorial into 1 minus x the whole to the power n minus k dx. This is equal to nck into n plus 1 into x to the power k into 1 minus x the whole power n minus k dx. Now let us do the verification. Consider the above function as I. Hence, I is equal to integral from 0 to 1 nck into n plus 1 into x to the power k into 1 minus x the whole to the power n minus k dx. To simplify this, we use the beta integral which we study in detail in the coming modules. Integral from 0, 1x to the power m minus 1 into 1 minus x to the power n minus 1 dx is equal to b of mn. This is equal to gamma m into gamma n divided by gamma m plus n, where m is greater than 0 and n is greater than 0. Hence, we can write I is equal to nck into n plus 1 into b of k plus 1 n minus k plus 1 implies I is equal to nck into n plus into gamma k plus 1 into gamma n minus k plus 1 divided by gamma n plus 2. Using the relation gamma n is equal to n minus 1 factorial, we get I is equal to n factorial divided by k factorial into n minus k factorial into n plus 1 into k factorial into n minus k factorial divided by n plus 1 factorial. On simplification, we get 1. Exercise 1. If x is uniformly distributed with mean 1 and variance 4 by 3, find p x less than 0. Let us solve the above as follows. Let x follow uniform AB so that f of x is equal to 1 divided by b minus a, where a less than x less than b. We have mean b plus a divided by 2 is equal to 1 implies b plus a is equal to 2. Variance b minus a the whole square divided by 12 is equal to 4 divided by 3 implies b minus a the whole square is equal to 16 or b minus a is equal to plus or minus 4. On solving, by taking b minus a is equal to minus 4, we get a is equal to minus 1 and b is equal to 3. Or by taking b minus a is equal to 4, we get a is equal to 3 and b is equal to minus 1. But in uniform distribution, we should have a is less than b. The solution for a and b is a is equal to minus 1 and b is equal to 3. Therefore, f of x is equal to 1 divided by 4, where minus 1 less than x less than 3. Hence, we can find probability that x less than 0 is equal to integral from minus 1 to 0 f of x dx. This is equal to 1 divided by 4 into x ranges from minus 1 to 0 is equal to 1 divided by 4. Subway trains on a certain line run every half hour between midnight and 6 in the morning. What is the probability that a man entering the station at a random time during this period will have to wait at least 20 minutes? Solution. Let the random variable x denote the waiting time in minutes for the next train. Under the assumption that a man arrives at the station at random, x is distributed uniformly on 0, 30. With probability density function, f of x is equal to 1 divided by 30, where 0 less than x less than 30. The probability that he has to wait at least 20 minutes is given by probability that x greater than or equal to 20 is equal to integral from 20 to 30 f of x dx is equal to 1 divided by 30 into integral from 20 to 30 1 into dx is equal to 1 divided by 30 into x ranges from 20 to 30, which is equal to 1 divided by 3. Here is a summary of our learning in this session, where we have understood the definition of uniform distribution through probability density function, described distribution function, explained moments, that is mean and variance, understood moment generating function, understood median and explained mean deviation.